So, let us first consider a two dimensional situation. Okay. Let us say what would be a 2D mean tangent diameter, let me call that as small h bar. What would be the mean tangent diameter for a circular object of diameter d? What would be h bar for this? You take any orientation, it remains as d. So, average, if you take an average, it will remain d. So, it will be the diameter of the circle. Now, let me consider another object. Let us consider a rectangular object of dimensions a and b. What is the mean tangent diameter for this object? Here we will have to do that full integration. Okay. Remember, in the 2D case, the density function for the orientation defined as f theta is the uniform density function given by 1 upon 2 pi. So, let me put this object in a coordinate system to understand this. So, all I have done is I have centered this object so that one end of the rectangle is centered about the origin. And the orientation is defined by the central axis with respect to the x axis. Now, this theta can vary randomly over 0 to 2 pi. What I will do is these are my two tangent lines parallel to the x axis, and the distance between these two tangent lines would be h theta. Okay. Now, I am using small h, so I will keep using small h here. Then the mean tangent diameter h bar theta is simply 0 to 2 pi h theta f theta d theta. So, what I need to do in order to do this integral? In order to integrate this, I need to express h theta in terms of theta a and b. Once I am able to do that, it will be a straightforward job to do this integration. So, let us try this. Let me draw some more lines here. Let us get different distances to get at h theta. First of all, let us take this distance. How much is this? Well, this length is b. So, clearly this length would be nothing but, if I consider this triangle, this would be b sin theta, right. Now, what about this length here? Then I will add up all of these pieces to get at h theta. Well, if this angle is theta, let me draw a perpendicular from here. If this is theta, this angle would be theta, this would become pi by 2 minus theta, then this would become theta. Okay, simple geometry. Hence, this length is nothing but, if you consider this small triangle, well, in this triangle, what is this length? This is a by 2. Hence, this length would become a by 2 cos theta. Similarly, this length would also be a by 2 cos theta. You can examine this. And therefore, I simply add up all of these. H theta would become a cos theta plus b sin theta. So, I have expressed the tangent diameter in terms of a, b and theta. Okay. So, now if I continue with this integration, this would become 0 to 2 pi. Instead of h theta, now I can write a cos theta plus b sin theta, and instead of f theta I put 1 upon 2 pi, 1 upon 2 pi being a constant, I take it out of the integral times d theta. I just need to integrate this. Now, also look at the symmetry of the problem. I really do not need to integrate all the way from 0 to 2 pi. I just need to integrate from 0 to pi by 2. If I do that, then instead of 2 pi here, I put here pi by 2, and then there are other, there is an integral from pi by 2 to pi, and then pi to 3 pi by 2. So, there are 4 such integrals. So, there will be a factor of 4 that will come out here. Okay. This is what that integral would become. All right. Now, this is a simple integral. This will give you the result. I will directly write the result now. This will give me the result 2 times a plus b divided by pi. Now, just think, let us go back to the Buffon's needle problem. Going back to the Buffon's needle problem, instead of throwing a needle, I throw these objects, rectangular objects of size a by b, okay, such that the diagonal, which is the maximum length of that object, is less than the spacing between these lines t. So, sometimes I will get an intersection, sometimes I will not. What is the probability of intersection in that case? Probability of intersection with the lines, this is nothing but h bar divided by t, okay, which is nothing but 2 times a plus b divided by t. Now, suppose I let a go to 0, what kind of an object this will become? This will become a line of length b. So, if I put a go to 0, my probability would become, there is a pi missing here, 2a plus b upon pi. This will become 2b upon pi t. You look at, this is exactly the same result that we had, the probability of a needle intersecting the lines. So, what we have actually derived is from both angles we come to the same solution. Another important thing to look at this result here, what is 2 times a plus b? is the perimeter of the rectangle. So, this is perimeter upon pi. It turns out, and we can prove it in a very general case, that for any convex object, okay, this object need not be a rectangle. It could have been, for example, an ellipse, or it could have been any other object as long as it is a convex object. So, for all convex objects, first of all, what are convex objects? Well, for example, this is not a convex object because it has some concavity. Okay. So, I am not talking about objects like this, I am talking about only convex objects. This is a general result, and it can be proved in a very general way, but we will keep this, we will not try to prove this in this course. That, I am sorry, this is not the probability, this is h bar. The mean tangent diameter in the two dimensional convex object is nothing but simply the perimeter of that object divided by pi. Okay. So, this makes things very simple. Now, you can imagine what is the mean tangent diameter for a semicircular object. What would be the mean tangent diameter for objects? There are sometimes you see these precipitates also. So, semicircular objects, it would be, take the perimeter of this. So, if its radius is r, so perimeter would be pi r plus 2 r divided by pi, that is the mean tangent diameter. Okay. So, this was one example that I put it in 2 dimensions. Let us take one example in 3 dimensions situation, and that also we will go through the derivation for that. So, for the 3 dimensional mean tangent diameter, again a sphere of diameter d, what would be its mean tangent diameter? It will be the diameter. Now, consider a cylinder. Cylinder of length L and radius r. What would be its mean tangent diameter? So, now we let us first define an orientation for this cylinder. So, the orientation for this cylinder, just like I had put the rectangle, I am going to put in a very similar way. So, take the axis of the cylinder, the axis of the cylinder makes an angle of theta with the z axis, and it makes an angle of phi with the x axis, the projection of the axis. So, different values of theta and phi would give you different orientations of this cylinder. Consider this as one tangent plane, and then there would be another tangent plane below the xy plane, which will make tangent here and will make tangent here. The distance of separation between these two tangent planes is h theta phi, and in order to get the mean tangent diameter, I will have to do now a double integral over phi and theta h theta phi times the density function in 3D d phi d theta, and remember that the density function just derived as sin theta upon 4 pi. So, again I will have to figure out what is h theta phi in terms of the radius of the cylinder, the length and theta and phi. Now, this problem is not as complicated as it looks. Let us try and visualize this as how will, first of all, the tangent diameter will vary with theta. If theta is 0 degrees, what will be the tangent diameter then? The distance between the tangent planes. If theta is 0, then the cylinder is upright, it is simply length, the length of the cylinder L. If theta is 90 degrees, it is lying down, then the tangent diameter will be 2r. In between it will vary. That is how it varies with theta. How does it vary with phi if I keep theta fixed? Let us say if I keep theta as 90 degrees and let phi vary, it does not change. If I keep theta as 0, it does not change with phi. If I keep theta at anywhere else, it will not change because of the symmetry of this object. So, it will be independent of phi, it is only going to vary with theta. So, we have just now reduced the scale of the problem. Now, we can further simplify it, that instead of looking at this diagram in 3 dimensions, let us reduce it down to 2 dimensions. Since it does not vary with phi, I position the cylinder such that the axis is in the yz plane and then take a section. So, what will I get? I will get a rectangle. So, I will get this is r, this is L, this angle is theta, okay. And the tangent planes would appear as lines in this 2 dimensional drawing, and the distance between these 2 lines is h theta phi, okay. Now, this actually reduces down to my problem of the rectangle to find out my tangent diameter, but the only catch is that here my theta is defined with respect to the z axis, there it was with respect to the horizontal axis. So, my cos and sine will get reversed, is not it? And I will get h theta phi to be this, again I can divide just like before. So, I need to find this distance, I need to find this distance, and this distance will be the same as this distance. So, this one would be L cos theta, this would be r sin theta, this would be r sin theta, right. And hence h theta phi would become L cos theta plus 2r sin theta. We can confirm this. We had said that when theta is 0, the tangent diameter should be L. So, if I put theta as 0, this term goes to 0, this goes to 1, h theta phi is L. if I put theta as pi by 2, this term goes to 0, this sin theta goes to 1, the tangent diameter is 2r, the diameter of the cylinder. Now, all I have to do is substitute this in this equation and get the mean tangent diameter by integrating it twice. So, let us do this partly. So, h bar so, I substituted h theta phi, I substitute f theta phi with sin theta upon 4 pi. So, sin theta will come here and 1 upon 4 pi I can take outside the two integrals being a constant, d phi d theta. Let us first integrate with respect to phi. If I integrate with respect to phi, see these are all independent of phi. So, integral with respect to phi would simply be phi with the limits and then put the limit 0 to 2 pi. So, what will I get? Just 2 pi, and 2 pi will come out of the integral. With now phi gone, you are left with theta. Now, looking at the symmetry of this object, I do not have to integrate all the way from 0 to pi. I can split this from 0 to pi by 2 to pi would be the same. So, I change this from pi to pi by 2. As a result, I will have to add another 2 here. So, what happens? All of this cancel out. So, you are now left with 0 to pi by 2, and let me break up this integral. L, I take it out, I have sin theta cos theta d theta plus another integral 0 to pi by 2, 2r taken out, I have sin square theta d theta. Now, this is a simple enough integration that I will leave it to you to perform, and the final result that you will get for the mean tangent diameter would be that h bar is equal to half of this term in brackets L plus pi r. From this I can get mean tangent diameter of couple of other objects. Suppose I let r go to 0, then what happens to the cylinder? It becomes a line. It gives me, for a line in 3D space, the mean tangent diameter for a line of length L is simply L upon 2. Suppose I let L go to 0, okay. In this case I put R go to 0. If I let L go to 0, L go to 0, then what I am left with? I am left with a disk of radius r, okay. So, for disk in 3D, so its a disk is a 2D shape, but it can take orientations in 3D. The mean tangent diameter for a disk is simply pi by 2 times its radius. In this way, the mean tangent diameters of various other objects have also been derived. Okay. So, I hope I made this mean tangent diameter clear. We will be using some of these results now in order to derive some of the relations in stereology which relate to surface area per unit volume, relating length per unit volume, number per unit area and so on. Okay. So, with this I close this lecture and we will continue in the next one.